So now we're going to start looking at the basis of something called the Euclidean algorithm or the division algorithm. So this lemma is a part of it. This says given two integers a with b greater than 0, then there exist unique integers q and r, where r is between 0 and b, including 0, so that a equals b, q plus r. The way this is phrased may seem unfamiliar, but it's really something that you have used before and know quite a bit about. So let's run through some examples to see how this works. So if we choose a is 18 and b is 5, then what this division algorithm is telling us is that there should be a q and an r, so that 18 equals 5 times q plus r, and we're going to figure out what q is, oops, I don't mean to write that, that is not true. And we have to remember that the r is supposed to be between 0 and b, less than b, greater than or equal to 0. So what are these things? If we want to complete this, r, the letter r, we're using because it stands for remainder. And the letter q we're using because we're thinking of it as the quotient. And so all we're doing is talking about a division equation here. We're saying that 18 is 5 times 3 plus a remainder of 3. Okay? And notice that that 3 is between 0 and 5, the way we wanted it to be. All right, let's do one more with maybe 18 and 6 for b. So this time, 18 is 6 times q plus r. Our q is going to be 3 and r is going to be 0. And notice that that r is between 0 and 6 as desired. All right, now it doesn't give us any condition on how a and b are related to each other, and so we can do this in a way that feels a little bit weird, but we can instead use a as 5 and b as 18. And so when we do this, we're saying, okay, 5 is 18 times q plus r. What are our q and our r? And remember that r has to be between 0 and b, which is 18. All right, so here clearly we want q to be 0 and r is going to be 5. And notice that's fine because all we needed was r less than 18. All right, let's do another example to show that it doesn't matter if we have positives or negatives either, although things can be a little bit strange in this realm too. All right, so if we use a as negative 18 and b is 5, again, our equation is a, which is negative 18, is b, which is 5 times q plus r. We need to figure out q and we need to figure out r, and our r has to be between 0 and 5. All right, so this time, q. You may want to do something like negative 3 for q. If we do that, then we have negative 18 is negative 15 plus, we're going to have to add a negative 3, which isn't allowed. Okay, so that doesn't work. What we have to do instead is sort of overshoot the 18. We need to do q is negative 4. That gives us 5 times negative 4 is negative 20, and now I get to add 2, and so my remainder is 2. This feels a little bit strange, but in order to satisfy that remainder r being between 0 and the b, we have to overshoot with that negative 4 for q and use r equals 2. All right. So this is the Euclidean algorithm. Say that again. This is a piece of the Euclidean algorithm. You're going to prove another piece to it as part of your homework. It's exercise 2 in the textbook. And then using the two of them, what we get is this Euclidean algorithm that tells us the GCD of two numbers. So GCD, here's the definition of that. A are two non-zero integers. The greatest common divisor of A and B, which we denote GCD of A and B, is the biggest of all the common divisors of A and B. All right, and when we say it's the largest of all common divisors, there are two things we're saying there. We're saying, first of all, that D is a divisor of both A and B. So D is a common divisor. And then the second part is how we mathematically write down the fact that it's the largest. What we do is we say if C is another one, if C is a common divisor of A and B, then D is biggest. So I'm going to write that a little differently. D is bigger than all other common divisors. Okay, so this is a little bit of a weird way to write down what we mean by biggest, but if we're going to be precise mathematically, we need to explain what we mean by biggest. And so what we mean is, if there's another one, call it C, then C is less than or equal to D. All right, you're going to use that idea in that proof I mentioned a minute ago, that other important piece to the Euclidean algorithm. Okay, so let's do a couple of examples of the greatest common divisor here. So, for example, the greatest common divisor of 7 and 28 is 7. The greatest common divisor of negative 4 and 14. So I need a common divisor, and I need it to be the biggest, which means here that's going to be 2. It's positive. Okay. The GCD of negative 6 and negative 21 would be 3. Again, it has to be positive. It's the of them all. And now just one more note about greatest common divisors. If the GCD of two numbers A and B is 1, that's a pretty special thing. It says that A and B have no common factors other than 1. And so we give it a special name. We say A and B are relatively prime. So we'll define prime a little bit later on. You know what it means, but we'll define it later. But A and B saying they're relatively prime is talking about the fact that they have no common divisors other than 1. All right, so before I end this video, let's talk about that division algorithm one more time. So we're not going to prove this lemma. It is proved in the book, but it has a lot of kind of fussy details in it that I didn't want to mess with. So feel free to read through that proof in the book if you want to. I think it's lemma 1.3. But for homework, you will be proving the other half to this that together become the Euclidean algorithm. And then you'll also be practicing that Euclidean algorithm.